Hello, everybody, and welcome back to Math 100. Today, we are going to study section 7.2, which basically has two completely different kinds of objects. And eventually, we'll see how connected, how unified those two concepts are, almost in a surprising way. So in this section, we'll start by, we will begin by studying what is known as the golden ratio, phi, or sometimes called phi. And then we will talk about the Fibonacci numbers, which really is a completely different topic. And then we'll see how they are closely related to each other. So remember that as you study these two concepts, okay? So section 7.2, the golden ratio and the Fibonacci sequence. The topics of section 7.2 are the golden ratio and the Fibonacci sequence. The main question is as follows: what is the golden ratio? And how is it related to something that seems to be completely different and coming from a very different area of academic discipline? So how is it related to the Fibonacci sequence? Okay, and the numbers in the sequence are called the Fibonacci numbers. All right, so first we go to this thing called phi. Now this looks like the symbol for the empty set. If you know what that is in mathematics, it's probably one of the most fundamental concepts in mathematics, the empty set. But this particular symbol here does not mean the empty set. This is the Greek letter phi. All right, so you know we call pi the circumference divided by diameter pi, right? The Greeks will actually call that letter of their own alphabet p, but we call it pi because it's spelled pi, and this is called the anglicizing of the pronunciation, of that letter pi to p to pi, and so this is called phi. And I will probably refer to this symbol as phi, as the Greeks do. But you will hear sometimes people calling it phi, because that's what it is often pronounced in America. You know, like if you have a phi beta kappa or something, that's not phi beta kappa, right? So you'll hear both pronunciations, phi or phi. I will probably refer to this as phi. And this phi represents, in our context right now, the golden ratio. Okay, this is a number, and this number happens to be about 1.618033989 ... Right? You basically have to know maybe the first 3 digits of it. Just remember, this is about 1.6 or 1.62. That would be great enough. Geometrically, it is defined in this way. Let me just go ahead and write this down first, okay? And then I'll talk about this. So the question is this. You notice here I have this phi by 1. So this rectangle on the left-hand side is phi by 1. The ratio of phi and 1 is, of course, phi. And so in the left-hand side, we have a rectangle representing this golden ratio, right? And the idea is this: find the length phi so that the rectangle of size phi by 1 shown on the left has the same side ratio if a square is added right next to it, to the side with length phi. Okay, so what in the world am I talking about? All right, so let me explain. You notice this picture here, and over here I have this rectangle here is phi by 1, right? So I'm going to write that ratio as phi by 1. This is the old proportion problem, just like in chapter 2, right? And then we're going to add this square. And now this square has to match right here. So this side is phi, and of course it's square. All sides have to be equal in length. That means this is also phi. This is a phi by phi square. So that means this length will be phi plus 1, right? Because this is 1. And so this bigger rectangle is phi plus 1 over phi, right? Remember, because this side is still phi, right? So phi by 1 is the proportion of the size of the rectangle on the left, and we want that to be equal to the side ratio of the bigger rectangle, which is phi plus 1 by phi. Okay, so the solution to this equation is what we want to call phi, all right? And if you do cross multiplication, you get phi squared. Oh, one more thing here. I write this phi like this. Some people write phi this way. It's the same thing, okay? So this is like the cursive and the print different, characters. It's like, B is like this or B is like this. So it's the difference between the cursive and the non-cursive writing. Just get used to it. Mathematicians write phi this way, and so it's my long habit to write phi this way, so I'm not going to change it at this point. And in some books, the phi will look more like this than this. Okay, so phi square, that's this times this, is equal to phi plus 1, of course, times 1, so that's that, right? And so this one, I mean, if you write this is the same as phi square minus phi minus 1 is equal to 0. If you try to solve this equation, right, so that's what we are looking for. If you try to solve this equation, the answer is going to be simple. Well, you can't factor this really, but you can use what is known as the quadratic formula, right? And so you can write your answer this way if you, and I'm not going to go through this, this is not an algebra class, right? But it's, well, I don't know if you know the equation. You have the coefficient 1, -1 here, and -1. So in order to avoid confusion, I will not show you these numbers, but here you have the coefficients 1, -1, -1. And based on that, this is negative b plus or minus square root of b square minus 4ac, 4 times 1 times -1. That's -4. So this will turn out to be -1 minus -4, which is +5. Okay, and then the denominator will be 2a, which is 2. And so if you abbreviate or if you simplify this, you actually get two answers. One is negative and the other is positive. If you insist that phi is positive, then you only have, of course, the one positive answer to this, and that answer is 1 plus square root of 2 over 2. Now, you don't need to know all the details of this, but I do want you to know this is approximately 1.618, okay? And I give you more digits here if you prefer. But the ratio is seen in lots of interesting things. That's a surprising thing about this. Now, so far, I have just given you a geometric definition. Okay, but it turns out this ratio 1.6 or close to 1.62 turns out to be appearing in many different pieces of art, different pieces of music, such as Mozart's sonata, piano sonata number 1. The lengths of the movements seem to reflect this number, and architecture definitely. And this goes all the way back to the Greek architectures from 2,000 plus years ago. Right, and in fact, it is considered the most aesthetic, which means beautiful, ratio for rectangles. Okay, so psychologists have done experiments to see, which is the most rectangular, which is the most aesthetic rectangular shape, and they will show long ones, the ones almost like squares and so on. And for some reason, people tend to choose a rectangle whose ratios, the length ratio is 1 and 1.62, or close to the golden ratio. So it's sometimes called the most aesthetic of all rectangles. Okay, so that is this number called the golden ratio, which has, again, if you talk to any people in art history or music history or musicology or the history of architecture, they will show you, they will tell you many well-known pieces, which includes or seems to include this point, not the point or the number, which is called the golden ratio. Okay, it is an important thing. And in fact, if you look up the golden ratio on the internet, you will probably have a lot and lots of pages explaining what that is and illustrate what kind of pieces of fine art include that. Okay, so that was the first example, or the first topic here, golden ratio. Okay, now number two, the second seemingly unrelated topic is the sequence of Fibonacci. What nationality do you think Fibonacci is? Okay. CCI ending is sort of a giveaway. Yes, he is Italian, but this goes like 800 years ago. This goes back a long time. And Fibonacci actually was not what we would call a mathematician. He was using mathematics to study, of all things, the number of pairs of rabbits. Okay, they seem to grow quickly, all right? And so he came up with some explanations to say, all right, so if you have one pair that reproduce after a certain number of weeks or months, then, of course, they will give, let's say, produce another pair, and now you have one, and then you have two, and so on. So the sequence that he proposed to describe the number of the population of rabbit pairs was to start with one and another one, and then the next number will be 1 plus 1, which is 2, and then the next number will be 1 plus 2, which is 3, and the next number will be 2 plus 3, which is 5, and so on. And so you start with 1, 1, and then write the sum of the two previous numbers. And in this way, you can write an infinite sequence, right? So you have 1, 1, 2, 3. What's the next one? 5, right? Because 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. How far should we go? This plus this is 34. This plus this is 55. All of these numbers appear in this sequence, and this whole sequence is called a Fibonacci sequence. Clearly, it's an infinite sequence, and it is an increasing sequence. And what else can you say about this? Each number is called a Fibonacci number. So 4 is not a Fibonacci number. 7 is not a Fibonacci number, but 8 is. 9 is not. 13 is. Okay, so any number that appears in this sequence is called a Fibonacci number. So here's a recursive formula. You see the first sequence, the first term of the sequence, which is F1, and F2 are both 1. Okay, that means you start with 1 and another 1. And then F sub n, the nth number, is the number preceding and the number preceding that. So you go back 1 and 2 places, and you add the sum. You find the sum of the two previous terms, and that is going to give you whatever that f of n is. That's the nth Fibonacci number. And so here we insist that n should be bigger than or equal to 3, right? Because the first two are defined as 1 and 1. Okay, now again, originally the Fibonacci, the scientist in Italy, was interested in growth of or in rabbit population. The numbers are seen in nature. Okay, so for instance, again, this is a part of what you will be doing for your either your homework or your online quiz. You're supposed to look up something about the Fibonacci sequence and where the Fibonacci numbers appear in nature. You will see references to things like pineapples, pine cones. How are they related to the Fibonacci sequence? Well, you'll have to look up some information online. Sunflowers, etc. Okay, so the Fibonacci sequence is something that is has its footprint in nature, not just in the mathematical classrooms. Okay, now there's an interesting picture we can draw. Okay, and in fact, I've drawn this for you because it's really hard to draw this while I lecture. And let me explain what's going on here. All right, so what we have here is this. I'm connecting something. Quarter circles. Okay. Of radii representing the Fibonacci numbers, comma. Let me stop here. Okay, so what am I talking about here? Do you see these quarter circles here? All right, let's go back to the deeper, the most innermost part of this drawing. You see this white square? That's 1 by 1 square. And then you have a gray square, which is also 1 by 1. You can see more details of this picture and the construction in the book. Just look up, section 7.2, and there is a paragraph about this this construction. And then you have a deep or dark purple, and you see that's 2 by 2. Okay, and then you have, so that's 2. This is 1. This is 1, and then you have a blue square. That's 3 by 3. And then you have green square, which, by the way, so this is 2 and this is 3, and that's why the green is 5 by 5. Okay, so now this is 5. This part here is 3. Right? You see this 3 squares here, tiny squares here. So the next one is 8. So the yellow square is 8 by 8. And then this is 8. Remember, this was 5. So the sum is 13 by 13. This is the pink, outside pink one is 13 by 13. You notice that the side length of each square is making the Fibonacci numbers, like 1, 1, 2, 3, 5, 8, 13, and so forth. The next one will be 21 by 21. You see where that is? Yeah, you see it, because this is 13, and remember, and this is 8. So if you were to add another square here, this will be 21 by 21. And then you draw the spiral using quarter circle. Quarter circle is 1/4 of a circle. That would be looking like this. So you start from here, quarter circle, another quarter circle, and then now this quarter circle has a radius of 2, and then 3, and then 5, and then 8, and this is 3, 5, 8, and this is 30. Did I make a mistake on here? Yeah, this is 8 and this is 5. So this is going to be a 13, right? And so that's 13 by 13. I apologize. This is 13 and 5. Maybe not. Hold on a second. Let me see if I can correct this. Yeah, so the green is actually 5 by 5. And so this is 8 by 8, which is your yellow one. And so I skipped the one. Orange is 13 by 13. That's right. Thank you. And so the orange is 13 by 13, and then you have the outside pink one, which is 21 by 21. So let me correct that. So this is 13, and this is 13. This is 8. So this is clearly 21, and because it's a square, this is also 21. Right. The next one will be how big? 13 plus 21. And that's going to be 34. So this will be a 34 by 34 square if you were to draw the next one. Right? But the point is, you keep connecting. You keep connecting these with a quarter circle. This is this quarter circle of radius 21. And then you will see that this thing here, this big triangle, this rectangle I just drew, this one here is, what is that? It's 34 by 21. Okay, and it is becoming more and more like the Fibonacci numbers. So maybe what I'm saying is that the the ratio of consecutive Fibonacci numbers seems to look like it's the golden ratio, right? And so that is the interesting connection between these two seemingly unrelated topics, the golden ratio and the Fibonacci numbers. All right, so let me go back and finish this sentence here. Now you know what I started to mean here, right? The connecting, okay. Connecting the quarter circles of radii representing the Fibonacci numbers, such as 1, 1, 2, 3, 5, 13, 21, and 34. what we get is we get an approximation or approximate spiral called the golden spiral, a type of logarithmic spiral. I'm not going to mention, explain what a logarithmic spiral is. Just remember, those are all spirals of this nature. And the point, it's called the golden spiral because it seems to resemble these squares, the rectangles become more and more like the golden rectangle. Did I tell you what the golden rectangle is? Of course I did, right? Maybe I didn't tell you what golden rectangle is. The golden rectangle is a rectangle of this proportion. The side length is phi by 1. So it's approximately 1.62 by 1. And that is called the golden rectangle. Any rectangle with that side proportion is called a golden rectangle. All right, this number, all these numbers that I'm drawing here, is related to, the Fibonacci numbers are related to the golden ratio. Now, you may think, well, these are the same thing, right? And that's because I'm presenting both of these in one section. And that's why you probably think, they're connected. But I didn't tell you this, if you are learning these two things, the golden ratio phi and the Fibonacci sequence, you probably wouldn't see any connections. Okay, this picture is the first hint that these two seemingly different things are connected to each other. Okay, so with this thing here, if I draw this picture here, it looks like, okay, this rectangle, or the bigger and bigger rectangles become, or seem to be more and more like the golden rectangle. Maybe you look at the ratio of these two Fibonacci numbers, consecutive two Fibonacci numbers. Okay, so these are just index numbers, 1, 2, 3, 4, 5, 6, 7, whatever. The third Fibonacci number is following 1, 1, it's 2, and then remember 3, and then 5, and 8. Remember, the next number is always the sum of the two previous numbers, the sum of the two previous numbers. 13 plus 21 is 34, and so on. What's the next number? Clearly, it is going to be 55. And then 55 plus 34 is 89. That's your 11th Fibonacci number. This goes on forever. We are not going to go on forever. Now, let's do the n plus 1th Fibonacci number divided by the nth Fibonacci number. So you take this number, you divide this by this. 1 divided by 1, no problem. 2 divided by 1. That's 2. 3 divided by 2, remember for this, which we are calling F4 divided by F3, I divide 3 by 2, and that's 1.5, right? And then next one, 5.3, which is 1.6666 repeating. Next one, 8 divided by 5, which is 1.6 period. And you notice here the numbers are getting closer to 1.62. Next one, 13 divided by 8. You can do this on your calculator. It's 1.625. Next one, 21 divided by 13 is 1.61538, and so on. Right? So what is going on here? And I will go ahead and finish this. And let's see, 34 divided by 21 is 1.6190. It's a little less than the golden ratio now. 55 divided by 34 is 1.61764. Oh, I'm sorry, 1.619 is actually a little bigger than the golden ratio, because the golden ratio, remember, was 1.618033984. But and so this is really close, okay? And as the numbers get bigger and bigger, guess what? It gets closer and closer. This one is 1.6181. And the index number gets bigger and bigger. As n goes to infinity, the ratio, here, let me go ahead and write this in with print. All right, so here's what I was going to say. As n goes to infinity, the ratio of two consecutive means back to back, Fibonacci numbers, which is f n plus, I'm going to write this later, okay? Here, let me go and write this, okay? What I need to write is f of n plus 1 divided by f sub n. Okay, so that is the ratio of the two consecutive Fibonacci numbers, right? And so this ratio approaches the golden ratio, which is phi, and that is 1.618033989 ... Okay, now that is the correct answer. You know, this is a solution to that quadratic equation I worked out on the front page. And you notice how close these numbers are here. Okay, and what this is saying is, and you can prove this mathematically, which we will not do here because that's beyond the scope of this course. But as you go further and further on this table, these numbers will get closer and closer to phi or phi, which is our golden ratio. So how, let's say this again. How is the golden ratio related to the Fibonacci sequence? The answer, as n goes to infinity, the ratio of two consecutive Fibonacci numbers approaches the golden ratio. Okay, approaches means it gets closer and closer to the limit of the number phi. All right, so this suggests the important lesson here. The golden spiral that we saw above will generate a rectangle. Okay, so I'm talking about the construction you saw up here. You know, it's getting bigger and bigger rectangles. So this will generate a rectangle closely approximating a golden rectangle, the ratio of phi to 1. Okay, so that is the connection between these two things. Again, remember, the golden ratio was born out of this equation, the mathematical geometric equation, while the Fibonacci sequence came about when some old Italian guy was studying the number of rabbits. And now we know that these two completely different ideas are actually very connected. In fact, you could argue it's one and the same. Right? So this is a surprising thing, and you see this in art and music, as well as in biological nature, such as pine cones and sunflowers and many other things. In fact, the Fibonacci numbers are so prevalent in nature that in Europe, they have a magazine, academic journal called the Fibonacci Quarterly. And every article appearing in that magazine or the journal is having to do with the Fibonacci numbers or the golden ratio or both. Okay, so that's it for section 2 of chapter 7. Your quiz, online quiz, will ask you to explain the relation between those two, which I just told you about, and then ask you to look up one of these or a couple of these. Yeah, just one, at least one of these topics briefly online, or if you are an old-fashioned researcher, you can go to the library and look at the printed version of Encyclopedia Britannica or something and find these topics, how they are related to each other. Okay, so let's do that. And I will see you later when we study, or when you are ready to study section 3 of chapter 7. Have a wonderful day, everybody.